Okay, so now if we choose x direction is the direction of rectilinear motion here. So as you can see in this figure here, that if you have F, which is applied on the mass, and A is the acceleration, and this is the coordinate system here, so X, Y, and Z. So in this case, the body is moving in the X direction only. And so in this case, because there's no motion in Y and Z direction, so the acceleration is only in X direction. So we know the acceleration in X direction is not equal to 0, but acceleration in Y direction is 0, and acceleration in Z direction is 0 here. So we can then write that summation of all the forces in X direction equal to MAX. So AX is acceleration in X direction, AY is acceleration in Y direction, and AZ is acceleration in Z direction. So this is the Newton's second law in X direction now, that summation of all the forces in X direction equal to MAX, which is the acceleration in X direction here. And summation of all the forces in Y direction is equal to 0, because the acceleration in Y direction is 0. And similarly, the acceleration in Z direction is 0. So summation of all the forces in Z direction is again equal to 0 here. Now, if we have a more complex case where the acceleration in X, Y, and Z direction is not 0, then we can write the Newton's second law in every direction now. So that will be summation of all the forces in X direction will be equal to MAX. Similarly, summation of all the forces in Y direction will be equal to MAY. And summation of all the forces in Z direction will be equal to MAZ. And now, again, the acceleration in this case will be, we can write this in this form, that AXI plus AYJ and plus AZK. So this means that the acceleration have three components in AX along the x-axis. So I is again the unit vector in the x direction, AYJ. So AY is the component of acceleration in the y direction, and J is the unit vector in the y direction. And similarly, AZK. So AZ is the component of acceleration in the z direction, and K is the unit vector along the z direction. And again, if you know the component AX, AY, and AZ, so you can calculate A by using this Pythagoras theorem here. So this is the magnitude of A. So AX square plus AY square plus AZ square. And again, the forces can be written in this form. So we can write that the summation of all the forces, which is again a vector here, can be written is summation of all the forces in x direction, I, summation of forces in y direction, J, and summation of all the forces in z direction, K. And then we can write the magnitude of this from its component. So summation of all the forces in x square plus summation of all the forces in y square, and then z square, and under the root. So again, we can use the Pythagoras theorem to calculate the magnitude of this resultant force. Okay, so because in kinetics you will be dealing with the trigonometry a lot, so therefore we will try to just revise a bit about trigonometry. I'm sure that most of you are already familiar with these concepts. So if you consider a force here, which is F, and if this angle is theta with the vertical direction, and if this is our coordinate system, so x, y, and z. So in this case, we know that the Fy in this case is this component here, and Fy in this case is F cos theta, which is the adjacent side, and the opposite side is fx in this case to theta, and which will be f sine theta in this case here. But if you consider this figure here, and again if you consider the same coordinate system here, so in this case then the fy, which is this component of force, will become f, which is again now the opposite side to beta. So the opposite side will be always f sine beta, and then the adjacent side, which is this side here, fx, this will become f cos beta. Okay, but this f cos and f sine is only applicable when this triangle is a right angle triangle. So when this is not a right angle triangle, so then we cannot use these laws. And then you consider this figure here. So in this case, we know that these three lines are not perpendicular to each other, and this is not a right angle triangle. So then we cannot use these laws here. We will need to then go to the law of sines and law of cosines. So in case of the law of sine, what we can write is that a, which is this the length of this side here, and then divide by the sine of opposite angle, so divide by sine of alpha, and this should be equal to b, and then the sine of opposite angle here, so b divided by sine of beta, and then we can again write that c divided by sine of gamma here. Okay, and now if we can also use the law of cosine here. So in this case, for example, if you know a, b, and you know the angle between a and b, so then you can calculate c here. So in this case, the c square will become a square plus b square minus 2ab cos of gamma here. So gamma is the angle between a and b. So if we know the a and b and the angle between a and b, which is gamma here, so then we can calculate c. Similarly, we can also write a square here. So if you want to calculate now a, and you know b and c and the angle between b and c, which is alpha, so which will become b square plus c square minus 2bc cos of alpha here. And similarly, for if you want to calculate b here, so b square will become a square plus c square minus 2ac cos of beta. You can use these equations also. Sometimes these will be helpful in solving numerical examples. Okay, now in kinetics, you will always be dealing with the forces. So mainly with three type of forces. One is a gravitational force, another one is spring force, and another one is friction force. So first we will describe the gravitational force, which is weight of the body. So as you can see in this case here, that if you have this system here, and if it is moving due to some force with some acceleration here, and this is our coordinate system, which is x, y, and z. So in this case, the weight of the body is always in the downward direction here. So in this case, the weight, which is mg, will be in the y direction. And again, we can calculate this w from this mg here. So m is the mass and g is the acceleration in the downward direction. But now you may have this sort of situation that you will have again the body is now moving in some inclined direction. And in this case, as you can see, that we can change our coordinate system. So we can in this case choose that the x is in the direction of the plane, because this will become a rectilinear motion. If you for this problem, if you choose this coordinate system, so then the body will moving in x and y direction, so it will not be a rectilinear motion. So to make this simple, we will choose the coordinate system along the direction of the motion here. But in this case now, if you look at the force, which is this force here, so which is in the x direction, which is fine. But if you look at the weight, so the weight is now in the vertical direction, but y is inclined, and it is perpendicular to this plane here, and x is in the direction of the plane. So now to solve this problem, we need to normally calculate the component of weight in the direction of y and x. So in this case, for example, if you are given the angle of this plane, which is this theta here, so then we can write this weight into split into two components. One is in the y direction and one is in the x direction here. And obviously, if this angle is theta, so we know that if you draw a perpendicular to a line, so which is this perpendicular to this line, and then this one is perpendicular to this line. So if this angle is theta, so this angle is also theta here. And in this case, you can see that this is again because adjacent to theta, so that will be w cos theta, and this is opposite to theta, so this will become w sine theta. And finally, if we have this situation here, that if in case instead of this angle you are given this angle here, so now again the weight is in the vertical direction. Beta is this angle. If this angle is given beta, so this angle is also beta here. And now in this case, this side, which is the wy, will become w sine beta, and then this will become w cos beta, because this is adjacent and this is opposite to beta. Okay, now we can discuss about the spring force. So the spring force is again important, and you will be using this in many numerical examples. So this is a common sense that a compressed spring exert a pushing force. That if you compress a spring, so it will exert this force on you on your hand, for example. And if you stretch a spring, so the spring will exert a pulling force, as you can see in this case here. So if you apply a compressive force here, the spring will exert this force, and if you stretch the spring will exert this force here. So these are the spring forces here, and the spring force for a given x. So this x is either the compression or stretch in the spring. So can be calculated using the Hooke's law. So this is the Hooke's law, that F is equal to kx. So F is the force of the spring, k is the spring constant, and x is the stretch or compression in the spring. So if you know the spring constant, and if you know the stretch or compression in the spring, you can calculate the spring force by using this this equation here, F is equal to kx. And the this k is what we call is the spring constant, and the unit of the spring constant is Newton per meter, which you can calculate from this equation here. So F is equal to kx, or k is equal to F divided by x, and the unit of F is Newton, and the unit of x is meter. So the unit of this k will become Newton per meter. So now if you look at this figure here, that if you have a spring here, and the length of the spring may be something like L, but in this case the spring is unstretched. There is no force applied to the spring. So this is the neutral in the neutral position. So if the spring is in the neutral position, there will be no force on this mass here, because the spring is in neutral position. So there is no stretch or there is no compression in the spring. Although the length of the spring is L, but this L will not produce any force in the spring. So to generate force in the spring, you will either need to compress the spring or stretch the spring. and which we are doing here. So in this case, if you apply this force on the spring and try to uh, uh, stretch the spring here, and the stretch in the spring here is x here, so then you will get a force on this mass, which is the spring force. And this force, obviously, then you can calculate from this equation here, that F is equal to kx, which is the Hooke's law, and k is the spring constant for this case here. And obviously, in this case, you are then trying to compress the spring, and if you compress the spring here, and the compression in the spring is x, so then again you can calculate the spring force, which is now will be this force here, the pushing force, and this pushing force will be equal to kx here. And now, because we are using this equation to calculate the spring force, so again, if you consider this this neutral position, that there is no stretch and there is no compression in the spring, so the spring force is 0 here. But in this case, if you try to stretch the spring through a distance x here, so x is the stretch in the spring, so we know that F is equal to kx here. You can calculate the spring force using this equation here. But now what will happen if you expand the this by 2 times? So if you change this from x to 2x, then the force will also be doubled, because we know that F equal to 2kx, because x is now 2k. So this will tell us that the spring force will become double if the stretch or compression become double, because this is what we call is a linear relationship between the x and F, which you can plot using this equation, this plot here. So what we say that if this is the x, which is the stretch or compression in the spring, and this is the spring force. So this is the spring force here. So if you if the stretch is 1, as you can see here, and this is 1, so now if this will become 2, the force will also become 2. So this means that that this is just the that this is 1x and 2x, so this will become 1f and 2f here. So this is just the showing us that there is just a linear law between x and f here. So just a straight line here. But this is not true in reality. In reality, if you see this law will not hold, if especially if the stretch in the spring become too large. So in reality, you may see these two type of spring. One is that uh, the the plot will become this way here. So this is what we call is a softening spring, and either it can be going in this direction here, which is what we call is hardening spring, and this behavior is what we call is a non-linear behavior of the spring. But we will in this course, we will not be discussing this non-linear behavior of the spring. We will be just discussing the linear behavior of the spring. So we will always use this Hooke's law to calculate the spring force. Now, another important type of force is a friction force. So if you consider that is the friction occurs when the unlubricated surfaces of two solids are in contact under a condition of sliding or a tendency to slide. So now apply horizontal force P, which continuously increase from 0 to a value sufficient to move the block and give it an appreciable velocity. So if you consider this case here, that if you apply force on this block here, and there are two surfaces. One surface is the block surface, one is this surface here. So if you look under the microscope, these two surfaces, it will look like this. That there will be these rough surfaces, and there will be these reaction forces at all these contact points. So R1, R2, and R3, and which we can write in this form if you want to draw the free body diagram for this case. So we know that the weight of the body is in the downward direction. The P is in this direction here. And then if you combine all these R1, R2, and R3, it will become R here. So R is just the summation of all these reaction. So it's the summation of all the reactions. So Ri and I equal 1 to, for example, N. So this will be, for example, R1, R2, and R3, and so on. And obviously all these are vectors. So this R is the summation of all these forces, and this is obviously a vector sum. So now we can see that this R can be split into two components. One is this F and one is this N. So N is the normal force here, and F is the friction force, which is opposite to this P here. So now what will happen if you apply this P? So P is our applied force, and this F is friction force. So if you apply P on this mass, so what will happen? You will get a friction force, and obviously if you increase P, so the friction force is increasing. So therefore you are moving along this path here, and initially the body will be stationary; it will not be moving. But at one point, when you will get the maximum friction force, and then the body will start to move when the applied force will become greater than this force here. So what will happen that the body will start to move, and this maximum friction force is written using this equation here, that maximum friction force is equal to mu s n, and then the body will start to move, and then you will have this friction force, which is what we call is mu kn. And before this point, because the body is stationary, is not moving, so we call this force here a static friction, because there is no motion. But from this point onward, the body is moving, and what we are seeing here is a kinetic friction. And the kinetic friction here is can be written in this form here, and we can see that the maximum friction force can be right using this equation here. The maximum friction force, which is F maximum, which is equal to mu s n, and this uh, mu s is what we call is the coefficient of static friction. Okay, and again here we have this force here, which is the Fk, which is the kinetic friction force, and which is obviously equal to mu k n, and n obviously here is the normal force. And in this case, this mu k is what we call is the coefficient of kinetic friction. And this mu k because as you can see here that that f maximum is always greater than fk. So this means that the and n is just the same thing. So this means that mu s will always be greater than mu k here. Okay, so now finally we will discuss about how you will construct a free body diagram for an accelerating body. So in this case, for example, you want to construct a free body diagram for this system here, which is inspection car run over the overhead cable. So this is our some inspection car, and which is running along this cable here. And again, you are given the some force here, which is a tensile force. So the free body diagram means that you have to isolate the system from its surrounding, because if you are interested only in this inspection car, so you will want to write the free body diagram for this inspection car only. The steps here are decide which system to isolate. So in this case, you may be interested in the cable, or you may be interested in the inspection car. So assume that we are interested in the inspection car here. We will isolate this system and draw its external body boundaries. So we will maybe just draw a rough thing here. So this is the rough diagram of this inspection car. And identify all forces acting on it. So now we have the inspection car. Now we need to draw all the forces. So the first force here is the T here, which is the applied force, tension. So you need to draw it here. Now obviously we also need to draw the weight of this. So the weight will be in this direction, W equal to mg. And again, there is some force, a contact force from this cable, which is holding this inspection car there. So there will be a force in this direction here, and you may call it, for example, P. So this is our all the forces that we identify on this system here. And finally, adding the coordinate system on the diagram. So now we will need to choose a coordinate system which will help us to simplify the problem. So either we can choose the coordinate system in the horizontal and vertical direction, but in this case, because the body is moving along this direction here, so it will be a good idea to choose the coordinate system in the x in this direction here and the y in this direction here. So then if we choose the coordinate system here, so this will be our x, and then the y can be, we can choose in this direction, which is again the perpendicular to this. So this is our coordinate system here. And then again, we know that the body is accelerating in this direction, so we will choose that the acceleration is in this direction here. So this is our free body diagram. Okay. Now to before going into numerical examples, let's summarize what we did in the today lecture. So we introduce kinetics, and we also introduce some application of the kinetics that where we can use kinetics in practical engineering problems. And then we discussed about the Newton's second law, that which is the base of kinetics. So this is the Newton's second law, that force, the acceleration of a particle is proportional to the resultant force acting on it, and is in the direction of this force. So F is equal to ma. And again, we also then wrote the equation of Newton's second law for multiple forces. So when a particle of mass m is subjected to the action of forces F1, F2, and F3, whose vector sum is delta F, sum F. then you can write this diagram here, that M is subjected to these different forces, and this delta F, summation F is the sigma F is the summation of all the forces, and A is the acceleration, and which should be in the direction of this resultant force. And we can also write the uh, the Newton's second law in x, y, and z direction. So if acceleration is not zero, then we will have Newton's second law in x, y, and z direction. But if acceleration in y and z direction is zero, so then we will have only Newton's second law in the x direction here. And finally, we also discussed that if you know that you can write the acceleration in this form here. So this means that acceleration is equal to, you can split this into three components: ax, ay, and az in I, j, and k direction, which are the unit vectors in x, y, and z direction. And if you know the acceleration components, you can calculate the magnitude of the acceleration using this equation here. And again, if you know the forces in x, y, and z direction, you can calculate the resultant force by using again the same procedure, or you can split the force into x, y, and z direction by using this procedure here.